Hi everyone, and welcome to the third and final lecture of this mini course in Chern-Simons field theory and invariants. Please, Pichai, go ahead.
Yeah, thanks, Daniel. So today I will try to give a flavor on three manifold invariants and also some interesting connections to topological strings and recent developments on knot quiver correspondence and so on. So that's the plan in this talk. And before I start, I can't do it. So I'll give a brief recap of what I was discussing in the last lecture. And then I'll get on to the invariants for three manifolds because Chern-Simons theory is in three manifolds. So we should be able to get the three manifold invariants from knot and ring invariants. That's the spirit in which the ordering is kept, assuming that we know now how to compute the knot and ring invariants. Then the other puzzling thing which has there around the turn of the century is that all these knot polynomials are all Lorentz series with integer coefficients. Integers, whenever you find, you should be able to give some kind of a meaning to it, like, either number of solutions or some kind of, the crossing number, linking number. That kind of interpretation we have not been managing to give for every coefficient in the polynomial series. If you write the workout skein relation or the explicit direct method, you find that these polynomials have integer coefficients and there is no topological meaning to those integers at the moment. And that's where around this turn of century, Kohanov came up with a nice categorification method. And then parallelly around this time within topological strings, Oguri-Waffa, Schwarz-Bukov-Waffa brought up a way of looking at it as counting the number of BPS states. So these are things which I will give you some flavor of how to connect with what I have been teaching you in the last two lectures. Okay. Yeah. And then three manifolds we will see can be obtained by surgery of knots in free sphere, and there should be an understanding of what is surgery within the topological string context. That is also something which we attempted probably 20 years ago. There are a lot of interesting ways of looking at it, so I thought I will give a flavor of that. And then finally, the recent developments on knot quiver correspondence. Okay. So especially we focused on finding the quivers for a family of knots called double twist knots. And I will end with some ongoing work and open problems. Okay, so that's the plan for today. Okay, so pictorially I have given you that there are two types of classifications in the knot context. Those which are arborescent, I told you arborescence can be seen as many three balls. Each one will have many four punctured S2 boundaries, and each of these pieces is what we call it as fingers. And you can also write a shorthand notation by putting some kind of a Feynman graph here. And these integers will take care whether it is anti-parallel. If it is anti-parallel, you put a bar, plus and minus for right-handed, left-handed. So it's a very nice notation to follow. And this gives us a very compact way of looking at arborescent knots. And in the last lecture, I showed you how these invariants can be worked out systematically. There are non-arborescent knots which cannot be drawn this way. And there are methods for this, but not so much efficient to compute for higher symmetric or higher representations of SUN. Okay. So, for example, this diagram can be redrawn this way. So if you redraw it this way, you can see that this has three fingers, and then you can play around with one three ball with a trivalent vertex connected by three fingers, and we can work out states for each of these fingers, and then combine by an inner product to get the knot invariant. Okay. So for any SUN, symmetric colors we can compute. The reason is that we know the braiding eigenvalues, and we also know from our work with Satoshi Nawata and Zodin Mavia, the Wigner 6J symbols for these special class of Arborus and all. So we can actually work out directly without going through scale relation. I hope this was clear in the last lecture. I'm just giving you a summary here. And I want to put in here one universal invariant. Okay, you can draw all the arborescent knot, as I said, as some kind of a Feynman tree. But this is a trivalent vertex, this is a four-valent vertex, and you can have all kinds of fingers. Okay, so you will put in parameters depending on how many crossings you're going to put, anti-parallel, parallel, side strands, middle strands, all those informations you can put in here. Interestingly, you should be able to write an invariant as a function of all these parameters. Okay. And if I set some parameters to be 0, it should shrink to one of those knots. Okay. So that's why I call it as a universal invariant. And this is a very challenging problem. Interestingly, we found a 7-parameter invariant. This was the work which we did nearly 10 years ago. But that 7-parameter invariant which we wrote, a tree which we constructed with 7 parameters, almost had all the 10 knots up to 10 crossings, except a few of them. Okay, this is, you can consider to be like measure 0 when you are looking at up to 10 crossings. So in some sense, this tree with 7 parameters was giving us a nice invariant in terms of 7 parameters, and we can tabulate which parameters being 0 corresponds to all the knots up to 10 crossings, except these. These were not included in that, couldn't be included. So the immediate question we had with the topical developments in the knot quiver correspondence is that for such a neat family, can I also say a quiver analog of such parameters in a neat fashion, was one of the questions which was, which we wanted to attempt, but that appears to be a very difficult problem. Okay. But, and then I also briefly went through that non-arborescent has various methods. It's just to put on record that we have some results on this for symmetric rank 2 up to 4-strand closure. So if anybody is interested, you can take a look at it. This is a work with Mironov, Morozov as a part of this DSK RFBR Russian Indo project, which we had from 2014 to 2019. Okay. Okay, so now I'm getting on to 3-manifold invariant. So if you recall, I did say that the Chern-Simons partition function is going to encode the information about the 3-manifold, and technically mathematicians have worked out 3-manifold invariance. They call it as WRT invariance. So this Z of M is proportional to this up to a proportionality constant. Okay. However, we want to obtain the Z of M using the link invariance. That is where Licorice-Wallace theorem comes into picture. Okay. Licorice-Wallace theorem says that you take a knot or a link, specifically a frame knot or a link in S3. Okay, and there is a procedure called surgery. Okay, I don't know, the surgery here is somewhat kind of in S3, you kind of remove, take a tubular neighborhood, remove, and so on. I'll show you pictorially what I mean. Let's take the simple curve in S3. You take a tubular neighborhood of the simple curve and cut it out. Okay. So what you have, once you remove it, there is a complement of that. If you take this as simple unknot, then it will be an unknot complement. And then you also have this tubular neighborhood of the unknot. Okay. So each of them has a toral boundary. Okay. Each one is a 3-dimensional manifold with a toral boundary. So on the toral boundary, you have these meridian and longitude in both. This is also a solid torus with oppositely oriented, and this is another solid torus of the knot, tubular neighborhood of the knot. You can see that if you just glue it back, then you will get it as if you're doing S3 containing the knot. But what we will do is we will do some kind of a homeomorphic map on the stored boundary, okay, in such a way that you get some complicated manifold, okay. So this is what is the simplest thing is you could take the meridian map to a longitude and longitude map to a meridian. In that process, you will be able to show that if you started with an S3, you will be able to show that it becomes an S2 cross S1. Okay. So this is the formal procedure which mathematician Licorice-Wallace theorem says. This procedure can be applied for various knots, and in the process, you will end up getting various three manifolds. And similar to the braids to knots, which was not unique, there were many braids which gave you the same knot and a closure. This also has two moves, which does not give you a new three manifolds. Okay, so if you do a surgery on this manifold, or if you do a surgery on this manifold, the claim is that you will get the same three manifold. Okay, on this, I mean this knot or this link, if you do a surgery of this object in S3 or this link in S3, you will end up getting the same three manifold is what Kirby move 1 is Kirby move 1 is stating. And Kirby move 2 is you can have one more disjoint and knot with extra twist. So I did stress this fact that frame knots, by frame knots, I mean you are going to fix the blackboard frame, which means you were not allowed to go out of the blackboard frame. Okay. So which means you can't apply Reidmaster move 1 to remove this. Okay. So this will be treated as a framing 1 and not. Okay. So that's why surgery involves blackboard framing, where you have to keep track that all the invariants which you are going to study or which we are going to use will not respect Reidmaster move 1. Okay. Under Reidmaster move 1, it will pick up a fact. Okay, so now using this Licorice-Wallace theorem, you should be able to quantify in an algebraic expression. How do I implement it? Surgery of frame knots and links in three sphere leads to a new three manifold. So I need to construct an algebraic expression where I will use these knot and link invariants, all possible colors put on these knot and link invariants, and I sum up over all the colors, because finally I need to get a partition function which has no observable sitting inside. One way of doing it is sum up over all the representations of those observables. And you should also make sure, if you want to call this to be a three manifold invariant, it should not change. This value should not change if I wrote it in terms of the frame knot or do a link which is related to that knot by a Kirby move 1 or Kirby move 2. If I write that invariant and linear combination of it, this answer should remain the same. Okay, so that is the requirement. Otherwise, it is not called as a three manifold invariant. Is that clear? Then only you will say, if it remains same under Kirby moves 1 and 2, then we say f of m qualifies as three manifold invariant. For surgery on a knot K, okay, formally, the three manifold invariant can be written as, you will have a framing factor because we are going to work with vertical or blackboard framing. And these S are this modular transformation matrices, which will be familiar in a conformal field theory. Okay. So for a specific knot, you sum up over all representation. This is the weightage factor times all the colored invariants. And if you confine to SU2, then you will sum it up over all the spins. And there will be a cutoff to the spin depending on what is your level K. Okay. If the level is, let's say, K equal to 5, then you cannot cross the representation number of boxes cannot cross 5. Okay. So those are the requirements, and you can write explicitly this three manifold invariant. I have put it as proportionality constant. You have to equate it and put a prefactor in such a way that if I take the knot K and do a Kirby move 1 and make it K prime, this invariant will change. and the prefactor will change in such a way that this answer will remain the same. Okay, so these are known, but it can be done. And what we showed is Chern-Simons partition function, which we find is actually related to this f of m up to some overall normalization, and that normalization is nothing but the partition function for S3. Okay. Okay, other puzzling thing which we wanted to look was the mathematicians had worked out this three-manifold invariance, but they worked it out using bracket polynomials. But bracket polynomials is for strands carrying fundamental representation, spin half representation of SU2. But they did, instead of doing sum up over all spins, they replaced the knot by a cable. Okay. Sometimes, you can replace every strand by 2 strands, that will be a 2 cable, or replace every strand by 3 strands, it will be a 3 cable, and so on. So that is what they did. The variant is not summing up over representation, but it is summing up over the cabling integers. Okay, so that's the only modification they did, and they had a nice answer. But we wanted to see that the Chern-Simons SU2 three-manifold invariant which we find is actually same as this licorice invariant, and that we could manage to do. In fact, with this mathematician, Swati Nayak, who helped me with validating them for various cable, we managed to show that this cabling is nothing but taking tensor product of SU2 fundamental representation. Okay, so that's one work which was showing, validating the mathematician's result is actually the SU2 Chern-Simons result. Okay, so particularly we showed licorice invariant matched SU2 Chern-Simons Z of M up to an overall normalization. So now coming back to some of the other developments in the turn of the century, as I stressed, all the colored Jones or colored homefly PT, if you do homefly PT, then you'll have 2 variables. If you do Jones, then A can be put as Q squared, so it will become 1 variable. Okay, so the colored Jones or colored homefly PT can be shown to be always a Lorentz series. Okay, and these coefficients, Cij coefficients, they turn out to be always integers. Okay, the coefficientsCijs are integers. We need to give an interpretation or reasoning for these integer coefficients. Okay, is that all right? So now I'm getting on to showing how Kovenov gave an interpretation, and also how an interpretation can be given from the topological string context for theCijs. I'm pausing for a few minutes. If you have any questions, the motivation, which is going to start with a slightly different away from Chern-Simons theory. Okay. Any questions? Okay, so let me get on to the reasons for the integer coefficients in all these non-polynomials. As I stressed, there were parallel developments 99-2000 in mathematics as well as physics, where they gave a nice way of interpreting why these coefficients have to be integers. Okay. So Kovenov brought in this concept of homological invariance. Sometimes it's called categorification program. Okay. And Oguriwafa counted them as counting the number of BPS states. Okay. BPS states are stable states in string theory. And both the ways, in fact, in the bigraded homological chain, one could show those coefficients, the integer coefficients can be accounted as a dimension of that homological chain space. Okay. So we'll review briefly. I'll just briefly give you a flavor, and you can take a look at some of these things. I still remember in 2009, Louis Kaufman explained these things in ICTP not theory conference. We had a school and a conference at that time. So it's just using statistical mechanics way of doing A splicing or B splicing. And this all at every crossing you have to do, and the final smoothing can give you one such state as this. There could be many states. And then you introduce two integers, n of s, which corresponds to the number of B slicings, and j of s for that state, this particular state, which is number of B splicings, plus you give a sign to the outer curve and the inner curve, and that defines for you the j. And formally, you could, for this particular example, you see that n of s is 0 and j of s is 2. And using this, formally, you can write your j of k, the Jones polynomial. Jones polynomial, if you remember, we put the knot with fundamental representation in SU2 Chern-Simons theory. You can write it as a dimension of this homological chain, where this space is the space of close but not exact. Okay, so this dimension will give you the homology of this bigraded chain. So it's really beautiful that there is a way to account for it. And here this coefficient is minus 1 over n. And what Konow said is that we can promote this minus 1 over n as t to the power of n. Okay. So I'm just giving you some all possible states and how to go from one to the other by the differential operator in this homology chain. And one could work out this Hn for each of these cases and put it in for trefoil and get the answer. But Konow gave this categorification, sometimes called as a homological invariant, involving the parameter t. And you can clearly see that if you put t equal to minus 1, then you end up getting, and this justifies why the coefficients have to be integers, because it's a dimension of this homological chain space. And t equal to minus 1 will give you the Jones polynomial. And there were many variants which were done in paper by Aganich and Shakirov, where they tried to change the variable to q and t, which is sometimes called as some kind of a deformation. It's deformed Chern-Simons, or refined Chern-Simons theory, but this works for only very specific class of torus knots. This doesn't really help us to get the invariance. These kinds of invariance is not combinatorial. Like I cannot do this direct evaluation the way I was teaching you for Jones or colored Jones. This needs to go through that exercise of writing all possible states and then accounting this and so on. So it is not as straightforward. But for some simple examples, there is a straightforward way of making a change of variable, and one could actually write the Konow polynomial. Okay. So we did struggle a bit for non-torus knots. I don't think we had a result for that. Okay, so let me give you a big picture about topological strings and knots. Okay, so all of us would like to be in 3 dimension, 3 space and 1 time. But you know that in superstring theory, we need 9 space and 1 time, and the remaining 6 has to be compactified. And for all, to make contact with phenomenology, it's always better to compactify on a Calabi-Yau space. Calabi-Yau threefold is complex 3 dimension or 6 real dimension with certain properties. I'm not going to get onto this. But as a target space as Calabi-Yau, so treat this quadrilateral to be like a Calabi-Yau space, which is 6 dimension, 6 real dimension or 3 complex dimension. You can look at submanifolds. The submanifolds are S3. Okay, that circle can be treated like a submanifold. And in S3, you can have Chern-Simons theory. And inside this S3, you can have knots. So I've just given you some kind of a cartoon picture of what is that 9-dimensional theory is R31 cross the Calabi-Yau, and people study topological string theory only on this target space. Okay. And we are going to now confine to looking at topological string theory where the target space is Calabi-Yau. Okay. So these were the works by Gopakumar Vafa and Ogri Vafa, and Kono, of course, did it for the categorification, which is these were all parallel works, but this topological string is only for these two. Okay, so any gauge theory, if you take any gauge theory, you can replace all the Feynman diagrams of the gauge fields by a double line. Okay, so you can try to redraw all these Feynman diagrams as kind of Riemann surfaces. So, and you know, in string theory, it is a theory where you sum up over all such genus G surfaces, right? So, Tooft made this proposal that any large N gauge theory should have a genus expansion, a closed string theoretic interpretation. So, let me take our case. Our case is what? We know that SU and Chern-Simons partition function on S3 explicitly. Okay. We know the value of Z of S3. Now, can I write this as a genus expansion in some parameter? And this one has both genus and poles. So this piece, you can interpret it as open topological string amplitudes, these coefficients. These can be interpreted as closed topological string amplitudes. So this is claimed for any gauge theory that the free energy of a gauge theory, log of the partition function is what we'll call it as field theory, that should have both open string interpretation, and in this case, it's a topological field theory. So we can have this open string equated to the closed string, but that you cannot do if it is not topological. Okay, so in some sense, topological field theory is very special, but Tooft's interpretation is log of any partition function of a gauge theory should have this closed string interpretation. Okay. What Gopakumar and Vafa showed is that this lambda is related to the Chern-Simons coupling and N, and you need to do SUN with N being very large. Okay, we can't do SU to Chern-Simons here. And then this T is the Kähler parameter, or it will account for the area of the P1. So you need to also know from this expression, what is the target space? Okay. So the target space turns out in the open string theory, like the deformed, people call it as a cotangent bundle on S3. In the context of closed string theory, it turns out to be the target space is actually a resolved point. Okay. I think I made should be a T. I think this one has to be a T. Okay. Okay, so there's a nice way in which the gauge theory can be explained. So this leads me to a puzzle. Can I get the log of partition functions for other three manifolds? Okay, which I know how to compute in terms of the knot invariant. Surgery of knots will give you other three manifolds. I wanted to attend this log of Z of M and wanted to get a series like this and give an interpretation similar to what is the target space and so on. Of course, this side I could say it is T star of M, which is the cotangent bundle of a three manifold. But this side is non-trivial. And I wanted to understand this, but we don't have still a very good insight other than S3 mod ZP. But we did get some interesting results using the Gopakumar Vafa, and also how to put knots in this setting was proposed by Oguri Vafa. So let me try and tell how to put knots in the topological string setup, and then how to combine these two information and try to write Z of M. Because once I know how to put knots, I will sum up over all representation and try and see whether I can get log of Z of M. Okay, so that is the motivation where we took up this in the context of topological string. Okay, so just to give you a picture in the spirit of your ADS CFT correspondence, so this is the Calabi-Yau, which is a deformed conifold. So S3 is non-trivial here. And what you can do is you can go to the conifold limit where the S3 and S2 shrinks to 0, and then you can resolve it where S2 becomes non-trivial. So coincident topological D-branes, you can wrap it on S3, and we claim like Malachena that coincident N D-branes, D3 branes will have a gauge theory. There it was super Yang-Mills n equal to 4. Here it will be Chern-Simons theory. And then this one is a closed string theory on a resolved conifold. So we can claim that this Chern-Simons theory is dual to studying closed topological string theory, A model topological string theory on a resolved conifold. Okay. It's just to give you a picture way of looking at it. Now, how do we? So far I did not put in knots, but now I would also like to put knots in S3. Okay. So basically take the knots, and what is the knot operator in S3? You basically, when you do the conifold transition and go to resolve conifold, you lose the S3 shrunk to 0. So you essentially take the expectation value of the holonomy of the knot in S3, and you choose the knot such that the knot is a common intersection curve between S3 and another Lagrangian tree cycle. Okay. So you have in the Skelebiov two three manifolds, S3 and LK, and knot is an intersection of these two. And now you try to write an operator in the string theory in the deformed conifold and take the expectation value of this. Okay, after conifold transition, so what you will view it as that because now you have a knot, you also have a probe. So you can take Chern-Simons with n coincident topological branes wrapped on S3. You can have m coincident branes on the Lagrangian submanifold wrapped on this LK. So after conifold transition, S3 disappears. So you still have these probe branes, which are M D branes are present in the resolved conifold geometry. But once you have D branes, it is no longer a closed string theory. It will be an open string theory. Okay. So this is the formal way in which you can find the expression which has been argued for the unknot, and the expectation value involves these FR, and these FRs have a very specific form. Okay, so these coefficients are integers, and sometimes these integers are called Labastido, Marino, Uguri-Waffa integers. It is still a conjecture that for any knot, these FRs have to have this property, and these have to be integers. It's not proven, but later on there were proofs that LMOV is an integer. The proof was given, but this integers, what they are is like counting the intersection of D4 branes with D2 branes. And it's beautiful to see that you get an interpretation for FR. But what is FR? FR involves some combinations of the colored knot polynomials. Okay, like FR for the fundamental representation is trivially the Homefly PT polynomial. And because we said FR should have this form, you see that these coefficients can be interpreted. The Lorentz series coefficients for the Homefly PT can be actually interpreted as counting the number of BPS states. Okay. So justifies integer coefficients as counting BPS states. Of course, this elaborate exercise was explained for the unknot, but doing it for any knot is a difficult task. But we can use Chern-Simons theory and give an indirect evidence what should be those, if you count those states per se from string theory, you should get these answers. This much we can say. So I would say it's a difficult task within string theory, but using Chern-Simons theory, we can predict those integers. And we tried to validate the Zoguri-Wafa conjectures for many knots. This was done with the Brother Sarkar nearly 25 years ago. And then there was a refinement in some sense that it is similar to what you saw for Kohanov invariant and Jones polynomial. There is some kind of a refinement which was introduced by Gukov, Schwartz, Wafa, and this can naturally be seen if you look at it from the M theory point of view. Okay, I'm not going to get into details. The upshot of this is that the Hilbert space of counting of those BPS states can actually be seen as this homological SLN homology, and this is a very neat way of connecting mathematicians or mathematical invariants, homological invariants to the topological string BPS count. Okay, so coming back to my question, I told you that now we know how to understand knots in topological string context, and we want to understand surgery of knots in topological string context. That was one of our aim. And this I didn't mention here with Praveena, who was my student in 2002, 2003. Essentially, in the large n limit, the partition function, this one will involve summing up over all representations of a knot invariance. And we could write in the large n limit a leading piece and a subleading piece. Okay. And one more assumption we assumed for the probe brains, we took that the expectation values are just not invariants. And using this and using Oguri-Wafa conjecture, we could actually show that this piece is the leading term, and that leading piece can be shown to be like an A model topological string partition function, just like the way Gopakumar Wafa showed for S3. We managed to show it for any 3 manifold, at least for some examples we tabulated, that the form was similar to this topological string partition function, where the Calabi-Yau looks like it still has one Kähler parameter. But we don't know what is the structure of that, but we obtained this result. So we were very thrilled that we could get the 't proposal of large n Chern-Simons on any 3 manifold, the log of the large n Chern-Simons on any 3 manifold, we could get the closed string theoretic interpretation. So we were a little bit interested to probe further. Then we came up with this puzzle that if you do this classical limit, which is almost K very, very large, the WRT invariant can be written as sum up over all possible saddles, okay, or all possible flat connections. But what we showed, so 't proposal is typically for the string theory interpretation for taking the free energy around a particular saddle, okay, any saddle, not particular saddle, any particular, you pick one saddle, take the log of that saddle, then you expect it to have a closed string interpretation. But what did we show? We showed that log of Z of M3, which is log of summation over all the saddles they see, has a string theoretic expansion or closed string partition function. So we showed this log summation over this. So we are stuck. We don't know what exactly is this duality. In the context of S3, you had only one trivial flat connection. So it was very straightforward that the summation is same as log of ZC. But even to go to S3 mod ZP, we still have issues about how to get this expansion, even though we have this expansion. Okay, so that's where we were stuck. But of course, this is still puzzling that this log of this had a very nice closed string partition function. Okay. Okay, just like we had this homological invariance where we introduced one more parameter T and we showed it to be a Lorentz series, right? The partition functions or the WRT invariance does not seem to respect that kind of a series. Okay. So is there a way of getting insight of finding this homological blocks for such three manifold invariant? Was the recent development where Gukov and a couple of authors have written interesting papers in 2017, which comes under this title as Z-hat invariants or homological blocks. So the partition function can be written over spin C connections with some linear combinations of Z-hat invariants. And interestingly, the Z-hat invariance will be a Q series. Okay. I'm not going to get into the details. What we did was we tried to understand the Z-hat series for SO3 and OSP12, the supergroup, symplectic, orthosymplectic supergroup. And then we found that they also respect, and we conjectured certain forms. But what was puzzling to us was that Z-hat series for SO3 was same as SU2 Z-hat series. And then we wanted to understand whether it is Lie algebra dependent or Lie group dependent. And we took it up as a next project where we looked at quotient groups and showed that it only depends on the Lie algebra and not on the group. The Z-hat. We gave a proof, formal proof that Z-hat B is only Lie algebra dependent. Okay. Okay. So now I'm going to get on to another way in which these LMOV invariants can be seen to be actually an integer. Okay. I'm just giving you a formal way of writing a generating series. These are the colored symmetric colors, and I'm going to confine to SUN. So sum up over all the symmetric colors, and this is with the weightage factor. So this is some kind of a generating series, which gives you the P as a function of X. Okay. You can also rewrite this because we know how to write PR in terms of FRs. You can convert and write it as a pleisthetic exponential involving this LMOV integers, which I explained when I looked at this Oguri-Wafa conjecture. And equivalently, the same series can be rewritten not as some simple summation, but involves some summation over D1, D2 up to Dn. And then this matrix will be an M cross M matrix. But these are the Q pochomers which we'll have. Okay. So this is a very non-trivial step. If anybody is interested, should look into this work by Kucherov, Gorowski et al. And only thing what I want to try and justify here is that this procedure of comparing actually will kind of help us to show that LMOV has to be an integer. Okay, so I'm not getting into the details. This is what is called as the generating series for the Donaldson-Thomas invariants. And we can use compare and contrast and show that LMOV has to be an integer. Okay, so I have not really drawn the homological invariant of a Holmblai PT can be drawn on a QA plane, but putting every node with some kind of the power of t variable. If you do that, then you will see that that diagram will have 3 nodes. Okay, so this is one of the proposal. You can look at the homological diagrams. The number of nodes will decide for the dimension of this B matrix, and this B matrix is what we call it as a quiver matrix, and you formally draw the quiver. So it's a 3-node quiver. Okay, and the t degrees for this Poincare polynomial is what we say, the homological invariant of Holmblai PT. The t degrees are 0, 2, and 3. And that is denoted as putting 3 self no self loops at one node, two self loop at the other node, and no loop at the first node. Okay. And of course, off diagonal elements in the B matrix, if it is non-zero between 1 and 2, you have 1 and it is symmetric. 2 to 1 is also 1. So you can write the 3 by 3 matrix, which is the quiver matrix for the trefoil. Okay. So I'm just trying to say that for every knot, we could do this exercise, and you can find at least one quiver associated with the knot K. Okay. So this is a very tedious exercise, but the conjecture is that there is going to be at least one quiver associated with each knot. And finding the Bij for those knots has been done for some simple examples. And we wanted to see whether we could write. I showed you a family invariant, a universal invariant. Can we write a quivers for the knot family? So this is something which we took it up. And this specifically, we did this double twist knots. And double twist knots diagram wise, I've shown you here. This side is just the twist knots. This one has 2s twist here and a 2p twist here. If you put s to be 1, then you get the twist knots. And you can formally write the invariant because it's an arborescent knot. Okay. So this is, we went through this exercise, and essentially we wanted to get the quiver matrix for these twist knots. Okay. So there's a procedure which is called this reverse Melvin-Morton-Rosansky approach, MMR approach. This can be systematically done, and we found certain pattern in this twist knots, and it helped us. Sorry, this slide did not come out very well, but it's a very systematic exercise following this, that we could find this explicit form of the quiver matrix. Okay, so what we observed was that the Alexander polynomial has this pattern for P full twist and M full twist, where the other one has a minus M. So this is the notation. And then using this, we came up with finding a formal parameter dependent, MP dependent quiver matrix. Okay. So explicit results, we have given it for 2 comma minus 2, then 2 comma minus M. And we kind of got a form for 3 comma minus 3. But writing it for a general case, we were not very, it was not very clear. So we just had these explicit answers. This was the work with Vivek Singh, Vivek Kumar Singh, Sachin Chavan, Aditya Dwivedi, Bhavani Mandal, and Siddharth Dwivedi. So this appeared 2 years ago. Okay, so let me conclude with what all we are trying on the ongoing works. So I did show you the finger way of looking at it. So you can have 3 fingers and draw a family. We can call that as a pretzel family. We wanted to understand whether we can get this quiver matrix. There are some interesting papers by Dmitry Koharowski and other Warsaw group on this permutohedra unlinking and linking methods. If you are interested, you can take the look at this Dimitri's lecture series. I don't know whether it's recorded in the Warsaw. You can check it out. And so we feel that they suggest some ideas for generating quivers for the pretzel family and other knot families. So can this procedure shed some ideas on deducing? Also, I did not talk about this analog of the z-hat invariance. There are also knot complement, which is also 3 manifold. There are f-hat invariants and fk invariants, and these fk also has a quiver correspondence. So some work is going on where we would like to get some clarity by mixing and matching with knot twisting regions and this homological diagrams, how they change, and also using these linking, unlinking procedures. So there's some interesting work which is going on. Hopefully within a month or so, the paper might appear. Other thing which we should actually look into it was Sachin had this on this quotienting group. We would like to see whether this can also be done for SO groups and the refinements. So we still don't have any clarity on this. Okay, I think I have, finished well in advance, probably because these are just advanced topics. But if you need any specific things to ask me, you can ask me. I can go to the board and explain. Okay, I'll stop here. And the other thing I wanted to say is that the unknot detection, you know what is an unknot detection, okay? So the thing is, Jones polynomial is one for an unknot. But so far, up to 20 crossings, whatever computation they do, none of the knots seem to have one as an answer, okay? So they believe that if you increase a large number of crossings, they should get an unknot polynomial. That's still a conjecture, but validation has still not happened. Okay. And hopefully, with this AI, machine learning, and high computing facilities, where we could go, use some reasonable number of crossings up to some million, trillion, up to 20 crossings, and generate AI ML to give some more information about the large number of crossings to see whether this unknot detection can be achieved at really high crossings. So these are some questions where the latest developments on AI ML, the topical ones where neural networks, machine learning tools might be useful. Okay, thank you.